Hello everyone, welcome to Lab 7 of our Introduction to Remote Sensing of the Environment using Google's Earth Engine platform. The topic for today is classification, validation, and accuracy assessment. Over the last couple of weeks, we've covered supervised image classification in Earth Engine using training data, and we've discussed the importance of validating our classification results. That's the topic for today. Just a reminder, if you're new to this channel, you can find this tutorial on GitHub, and the link is in the details tab of the video. You'll need an Earth Engine account, and we'll be working within the Earth Engine environment, which is located at this URL. This lab builds on a series of 6 other labs. You can find those links over here. The objective for today is to learn how to evaluate image classification results and conduct an accuracy assessment using independent validation data. First, we're going to recap. We're going to load up an image. We'll use a Landsat 8 image for a specified date range. And I think for the class today, we'll use Perth as an example, Western Australia. So we can just navigate to Perth using Google search bar, zoom in, and the first thing we want to do is drop in a geometry and rename that to ROI for region of interest, and we're going to use that to spatially filter our search for an appropriate image. So our first line of code we'll copy in and paste here. And let's just read through this again quickly. We're going to create a variable image, and that image is going to be pulled out of the image collection Landsat 8 Tier 1 surface reflectance. Remember, you can substitute this in for a different collection, different satellite if you want to. We're going to filter that image collection using filter bounds to intersect with our ROI. We're going to filter by date to find a cloud-free image over the area. And we're going to sort by cloud cover. Remember, the sort function works by default in ascending, so from the least cloudy to the most cloudy image. And we want to return the first image from that. So we're going to run that. We don't see any immediate feedback because we haven't asked for anything. If we want some information, we can print that image to the console using the print command. Run that again, and you'll see it pops up over here. And we know that this is an image collected on the 8th of June. Okay, now the next step is then to load up a true color composite of that image using map add layer. So map add layer, we're going to load the image to the map view. We're going to specify the bands. We're going to use the red, green, and blue to make a true color RGB composite. And that'll be loaded in our layers tab over here. And here it comes. Let's zoom out. So a nice, relatively cloud-free image over the city of Perth. Quite a nice range of things we can look at here. We've got ocean, city, we've got some forested areas, as well as some agriculture out, a little out of the city here. Okay. Again, I'm going rather quickly through this now because we have covered this in previous labs. So if you need a slower recap, please go back to labs 4 and 5 especially. We're going to, the first part of our collection, we're going to focus on 4 different land cover classes: water, city, forest, and other. And we're going to collect some training data. A great tool for collecting training data is this little rectangle over here. And under geometry imports, we're going to click add new layer. We're going to do that 4 times because we're going to be using 4 land cover classes. We're going to rename those in our import section. And I'm going to call them, I'm going to put a small t in front of each class, as this is our training data for water, training data for city, training data for forest, and training data for other. Don't forget, when we are creating these training data sets, it's important to change the geometry type to a feature collection, as well as adding in a property label. And I'm going to use land cover again as the property label. And we also need to assign a numeric value to each class. So water in this case will be 0. And I'll then come and do the same for city. But I'll now label this with a 1. And forest I'll give it 2. And other will be a 3. Okay. Now once those are done, we can zoom in a bit closer. And if you click on the import over here, you'll see that it becomes selected. It's shown in bold. That means now if I draw a polygon, it's being drawn for that particular class. If I switch over to city, for example, I can now draw one of those. Let's do forest. And what should we use for the other class? Maybe just something like this. Other. So that's quite a vague class. We'll see what comes up with that. Okay. Now that we've drawn those, we can exit. We can, of course, collect more training data over bigger areas. And we would want to do this in a stratified random way across the whole image, ideally. But the next step, after we're happy with our training data, we need to merge these classes into one feature collection. So I do that with this command here. We're going to create a variable class names, and we're going to do it like this. Class names is equal to training water merged with training city, merged with training forest, merged with training other. And I'll print that to the console just so we can check. You can see we've got these 4 polygons and they're each assigned a land cover class, which is great. And that means we can move on with actually using this training data to sample our image. So in this next step, we're going to extract training data from selected bands of the image and print the information to the console. First, we're going to create a variable bands, and we're going to choose the bands that we're interested in. I've chosen here from band 2 through to band 7. Then we're creating a variable called training, and we're going to then select these bands from the image and then use the sample regions function for our feature collection class names and intersect different land cover classes with these bands. Scale is 30 because that's the pixel resolution. And then we're going to print that training data to the console. That's going to pop up over here. So after we hit run, that information will pop up over here. And you'll see now that if we come into properties, under features rather, we can come into each pixel there's a lot of features in this list. We can see that there's 7 properties, and we have the reflectance values for each band, as well as the land cover class that we've assigned from our training data. So if we come down to one of these others, we'll see that that should be a different class now. Actually, we've got 4,000, over 4,000 pixels sampled here. So if we come right down to the bottom, now we'll see that that's land cover 3, and these are the reflectance values. So that's a nice training data set that we've built up, and that's all in the variable called training. If you exceed, if your sample areas exceed the 5,000 pixel limit, you might, often it'll still run, you just can't print it to the console. Okay, the next step then is to train our classifier, and we're going to just use the cart classifier again, regression tree classifier. Remember, if you want to change an experiment with different types, you could just substitute cart for random forest or SVM, but you might want to then look into the default settings for these classifiers and experiment a bit more. If I hit run now, we haven't asked it to print anything or map anything, so not much changes, but we don't get any errors. That means that our classifier has worked. We've trained the classifier. The next step is then to run the actual classification. So now we're using the training data to make predictions about pixels that we haven't actually seen yet, that the classifier hasn't seen. So we're creating a variable classified. We are selecting the bands we want from our image, and we're running the classification using the classifier that we established over here. And we can then add this classified map to our screen using the command like this. So just a note here, added in here map center object. That's just going to center the extent of the map to the bounding area of our training polygons. We're going to map add layer classified, so we're adding the classified map to the view. Important here is that your min and max match the number of classes you have. Remember, starting with 0. So 0, 1, 2, 3. For 4 classes, this ranges from 0 to 3. And the palette, this depends. You can specify the colors you want to represent your classes. We established our classes as water, city, forest, other. So I'm happy with those. We hit run. We should come up with a classified map. And here it comes. So from a very quick eyeball, it looks pretty good in some places, but obviously we have some errors creeping in, where we have forest and city occurring in the ocean. Obviously points we need to focus on, and collecting more training data will help with that. But what I want to explore now is, aside from just eyeballing a map and saying, does it seem reasonable or not, how do we quantitatively assess it? And that's the focus of this lab, classification validation. So what we're going to do is we need some independent validation data to test against our classified image. And typically we could do this by going out in the field with a differential GPS, collecting a whole lot of points on the ground where we know exactly what this land cover class is. But we can also do that by collecting another set. We could sort of subset our training data, reserve some as training and use some for validation. But what we're going to do today is just collect another set of validation data. So I want you to collect 4 new land cover classes, but this time we're going to call them, so we're going to add 4 more layers here. I'm going to turn off the map for now, the classified map. And I want you to call these V water for validation water, V city for validation city, V forest for validation forest, and V other for validation other. Importantly, we need to change these all to feature collection, and we need to give them the same land cover properties as we did for the training data. So city is a 1. Watch your spelling. City we've done. We need to do forest. Forest is a 2. And other is a 3. It's up to you how you do this. You can use the rectangles, or you can use the little dropper icon. Let's start off with water. So V water highlighted. I'm going to use the little rectangle tool. Let's zoom in. Make sure that what you collect is in the image. So let's just collect those. For example, city. If you make a mistake, you can exit, click, and delete. Let's come to the bigger city. So we can see city itself is quite a diverse class. We have the suburbs and the more downtown area. So let's go the city, collect a few pixels in there. Again, forest, come into the hills here, not doing well with my mouse today. And again, the best approach would be to spread these out over a more diverse area. Let's just come out of here a bit and get into this agricultural land and get that last other class. Okay, so essentially we've done the same thing as we did with the training data, but this we're not going to use for training at all. We're only going to use this for validation. Again, we need to merge these into a common feature class. So we're going to run the line variable validation names, v water, v city, v forest, v other. We're merging them into one feature collection. Now, after having done that, we can actually generate our validation data. So we're creating a variable called validation. And it's very similar to how we collected the training data, except instead of sampling the image, we're going to sample the classified map. We're still using sample regions, but we're intersecting this classified map with our validation feature collection. And we're going to ask it to pull out the land cover assignments. So if I run that, if everything works, it should pop up in the console, which it does over here. And I've got too many features, so I need to just make one of these a bit smaller. It's probably this one that was too big. Just try and run that again. Okay, that's better, under 5,000. The important thing now is that if I come into this feature list and we look at the properties of one of these pixels, we'll see that it has two properties. It has the classification class, that's from the map, and then the validation land cover. So in this case, we have agreement between the map and our validation data. So that's a match. But we have this for 4,000 pixels in our data set. So that's our validation data set. How do we actually explore it? We can use these commands here, test accuracy. So we'll paste that in here. We're going to compare the land cover of your validation data against the classification result. We're going to create a variable called test accuracy, and test accuracy will be equal to validation, that's this variables. We're going to create an error matrix between land cover and classification. We're then going to print out the validation error matrix, and we're also going to ask it to return the overall accuracy. So let's run that. And two important things come out over here. Firstly, we get the validation overall accuracy. You can see it's very high, 88%. But the overall accuracy is not a very good measure of map accuracy. What we really want is access to the confusion matrix, and that's what we have here under this validation error matrix printout. This is basically the reference data, the validation data, against the classification. And using these are counts of pixels that are in agreement between the classification map and the validation data. We can use that to construct the error matrix and calculate the users and producers accuracy, look at the emissions and commissions on a per class basis. So you'll want to copy this out into a spreadsheet and calculate those different metrics. And don't forget, like we covered in the lecture, once you have this error matrix, you can also calculate the kappa coefficient, which will give you a more rigorous indication of how accurate your results are. Before ending off though, just important to reiterate that these accuracies depend very much on how good your validation data is. The way I've collected it now is not perfect. We would want to distribute these points over a much bigger area. And same with the training data. I've collected them in very small locations now for a large image. You'd want to spread them out in a much more stratified random approach. So that brings us to the end of today's lab. Your last task is to export your matrix for further analysis, calculate individual class accuracies, look at your different user and producers accuracies for each individual class. I hope you found that useful. Remember, you can find the tutorials themselves on the Gears GitHub page, and don't forget that we have a whole series of videos covering just different aspects of introductory remote sensing. So thanks very much, and see you next week. Cheers.